Good afternoon, fancy meat computers. Ha. More powerful. You already hold my job in your hand. Yes. Yes. But you could always have more power, right? It's how many giga jobs am I in control of right now, right? Instead of gigajoules, energy, power. This joke got away from me. Oh, I didn't see the exam schedule for this class. Yeah, so, that's because of the way that we're going to be having the exam. It's slightly abnormal. So, there's kind of a story. There's kind of a story to it. So this is the story. At the beginning of the pandemic, I decided to do something a little bit different with my tests and examinations than pretty much everybody else was doing. I hate the idea of proctoring, so I decided to go for like a 24-hour window of submission take-home type test. This was, hopefully this, the intention was originally to have this greatly benefit the people who were out of territory, right? People who have to go on, people who live in different time zones, right? So nobody's necessarily disadvantaged by the fact that they might live in, China or India or Europe or anywhere else. So I did this for a while, and the way I was doing it was I was asking the registrar to schedule me a slot, and then I would take that slot and sort of do it over the day that I've been scheduled for, because generally speaking, the registrar won't book, more than one exam per day, hopefully most of the time. So it turns out that I was actually in violation of procedure, and that there is actually a procedure for that. What I have to do is I have to wait for the official exam schedule to come out, not submit an exam request for my classes that I want to do this with, and then submit make a manual request for them to calculate which day is optimal to have a take-home test. So that's what we're doing. Your exam is not appearing in the regular schedule, but we will have an exam. It will be at some point during the exam season. But yeah. So that's, that's how we do it. Some people overdo it and spend the whole 24 hours, though. Yeah, but that's their choice, I generally have this impression, people tend to work faster when there's a tighter timeline, a tighter deadline. It's kind of interesting. Sometimes with, something like a hackathon, if it's a 48-hour hackathon, less gets accomplished than if you have a 12-hour hackathon where you don't have to stay overnight, because people aren't, tricked into thinking that they have more time than they actually have. And I think that sort of it's a little bit liable to this. But, given that this is still a hybrid semester and that we do have people taking the course from all over the planet still, although I think that's decreasing as we're approaching the winter semester, I'm going to choose to continue to do it this way. So that's that. It is what it is. But yeah, so that's the deal with the exam. There will be an exam. I'm waiting to hear back from the exams records office to know when would be the optimal time for all of you for that. Should be a reasonably easy database operation. But yeah. So, yes. So that's all that. Let me see if we have any announcements. My understanding... Oh, okay, yeah. So I posted a helpful video. Those of you who are sort of, probably a great number of you have not started Project One yet. If you're sort of having some difficulty like understanding how to get started on it, I posted a link, which is a video to a it's a link to a video of one of my increasingly favorite YouTube channels called Computer File, where they like interview the they interview the Greybeards and like ask them why C was developed the way it was and stuff like that. And one of them I saw this video on what is a monad, and the way that they set up this video is by developing in Haskell a very, very, very small, compact expression language, which, while in content, it's, it's definitely not our long familiar UAE system, but the approach that they use to develop their expression language is, I would say, just about exactly the same as the approach that I am expecting you guys to use on the assignment from a written description. So or the project on a written description. So probably some of you will find that helpful. If you don't find it helpful, it means you already knew how to do it, basically. And that's just like the first 4 or 5 minutes of the video. After that, it gets into like stuff that's still very, very useful to know, but not necessary for Project One. But yeah. Don't say I didn't give you any help. So, we're going to talk today about primarily church booleans and church numerals. We'll see if we get through all of it. I'm inclined to believe that we'll get through all of it, but things are going to get pretty mathy, so hold on to your butts. So, now that we have our new mode of computation established, let's start reconstructing the elements of untyped, I almost thought was universal, untyped arithmetic expressions, starting with the Booleans, because they're the easiest. We can define true and false as follows. We use true, TRU, and false, that's FLS here, to avoid confusion with true and false of UAE. So we're, not strictly necessary that we do this, but later on when we try to develop a correspondence with, existing Boolean values to enrich the calculus, it'll be useful to be able to distinguish true and false lambda expressions from, like, the true and false of UAE or, propositional logic. So that's how we're going to rename them. So, this is true and false in lambda calculus, and this is really going to bake your noodles. Lambda t, lambda f, return t. So true is you accept 2 arguments and return the first. False, floss? Yeah, okay, we'll call it floss. No, I'll keep calling it false. That'll make things more difficult than they need to be. Lambda t, lambda f returns f. So, lambda expression for true takes 2 arguments, returns the first one. Lambda expression for false takes 2 arguments, returns the second one. This is a very different way of thinking about true and false. Normally, we're used to thinking of them as, like, values, literals. We don't really think of them as things that do things, right? False doesn't do anything. It's, it does, like, other things do things with it, not the other way around. It's like, what does the number 4 do? Nothing. It just sits there. It's only useful and interesting in the context of the things that operate on it. But as we go through this, we're going to do some examples, and we're going to see how this actually makes a whole lot of sense. But you have to also keep in mind, this is a design decision, right? We can develop a Boolean system. Like, hypothetically, we could develop a whole bunch of different Boolean systems using lambda calculus. It's that general. But with this guy, like, this is the classically accepted way of doing Booleans inside of lambda calculus. It is sufficient. It does all of the things Booleans need to do, and therefore, if it's sufficient, and, you know, there's nothing substantially better than it, then it persists, just like the QWERTY keyboard. So, wait, what? Our definitions of Boolean values won't make a lot of sense until we show how they're used. Consider the following lambda expression, reproducing UAE's if-then-else term. So, after I went to all that trouble to get that pen to fiddle with, I'm going to sneeze. Ooh. Ooh, that was... Ooh. Oh, yeah, okay. I thought my rib was popped back into place, but it wasn't. Ugh. Ugh. Ouch. All right. Let's see if we can get through the rest of the lecture. Ugh. Thank you. Oh, that's not a bad delay, actually. So our test function, which performs if-then-else, takes 3 arguments and just applies them to each other. This is kind of like a triple identity function, really. So it's like, okay, all right. What? Thank you. Dankeschön. So, let's try it with true, see how it works. So, remember our use of if-then-else, right? The first thing is the condition. The second 2 are the things we're selecting between. So we don't necessarily like need true or false values here. We could just have like general lambda expressions u and v. If I live stream on Twitch, I could have low latency mode. Yeah, but you know, then I'd have to get a low cut blouse, and you know, it's just not in my current wardrobe. Jokes about Twitch. I tried all right, let me see. Stream settings. Let's see here. Is there a low latency mode? Oh, that's not what I want at all. Is there a low latency mode? Stream latency, normal, low, and ultra low. This is new. It used to be just like normal and high. Okay. Well, that's interesting. I'm gonna have to try that. Next week I'll try low latency mode, see if we can improve that. Like recently, like at the beginning of the semester, they like added a bunch of things like the ability to do polls. I guess they added that at the same time. I didn't read the changelog, like evidently. But anyway, so this is how it works. With t1 equal to true. So we apply. First, we perform the first application. We substitute true for all occurrences of t1. That puts it in here. Next, we apply u to t2. We get it there. V gets t3 gets replaced with v, so you get there. Now let's expand the definition. Ultra low kills quality, but low is good. Okay. Have to try it then. So, so then we expand the definition of true, which is, of course, lambda t, lambda f, t. So we apply the first argument. T gets replaced with u, so you end up with u. Then v gets replaced with f. F is nowhere, so it just winks out of existence. And yes, I see I have unequal brackets here. Whoops. I'm not. I'll fix it afterwards. So then you get u as a result. And remember, kids, with if then else, if true, then you take the first one, which is t2, which is what happened here. Same thing with false, right? You apply these three guys, you end up with false uv. You apply u, you get nothing because t isn't in this one. You apply v, that actually does work because once you take the t off of this, this is an identity function, so you end up with v. So if then else isn't really doing anything itself. It's the definitions of true and false that sort of encode the functionality of selection, right? But we could have known that by noticing of true and false that it's, select this one, select that one. But yeah, so so far so good. If you have any questions, please ask them now. Uh-oh. Oh, there we go. This stuff is going to start to increase in complexity quite quickly. Good. So, Boolean operators. Adding pieces to the lambda calculus is very different from adding pieces to UAE. Joe notes, reading lambda simplifications feels so weird compared to normal math, lol. Yes. Oh, full screen, yep. Thank you, Yusuf. Yusuf has my back. Rationale for selecting lambda, this guy, f.u, and not v. Well, in this one, right, you have to do these things in the order that they're presented, right? So u gets applied to t, which means that this t is replaced with a u. Once this v hits the f, there's no f in here to replace. So the is sort of like the lambda goes away, it disappears, and all you're left with is u. Kind of hard to believe this is equivalent in power to Turing machines. Oh, just wait. Oh, just wait. So, adding pieces to lambda calculus is very different from adding pieces to untyped arithmetic expressions. To expand UAE, we need to add additional terms and evaluation rules, right? The more terms and evaluations we add, the longer and more complicated our proofs become, as I'm sure all of you are finding out with assignment 3. Expanding it, like, it does take a certain amount of brain power to expand, like, say, the proof of determinacy so that it takes into account 4 more terms. By contrast, when we added Booleans to our lambda calculus, nothing actually had to be added to the language itself. We do not have any additional terms, right? We have instead defined some replacement expressions, right? We've defined some lambda functions, we've given them names, but this is still lambda calculus. So, yeah, if you're watching this in like 144p, I'm sorry, but there's nothing I can do about it. I pay for very good internet. This is not happening on my end. So, by the way, attendance seems pretty low. You guys got a test or something? So, true and false are not terms, but labels for lambda expressions that were already valid terms. As opposed to UAE, when we add something like is0 to UAE, we need to increase the size of our set of theorems, we need to increase the size of the set of terms, we are modifying the language itself. We can describe Booleans in lambda calculus without needing any additional terms. So why is this important? This is a very useful and important property of lambda calculus, and one of the reasons that it's so popular. It's one of the reasons that it's like, as models of computation go, in terms of popularity, you've got Turing machines, and then you've got lambda calculus. It's not as popular as Turing machines, of course, but it's the next most popular one. So, conservative extension. Consider two theories. Theories are collections of theorems. T1 and T2. We say that T2 is a conservative extension of T1 if every theorem of T1 is a theorem of T2, and any theorem of T2 in the language of T1 is already a theorem of T1. So this is true of the relationship between lambda calculus and lambda calculus with these additional Boolean terms that we've added that aren't real terms of the language, but just relabelings, right? We did not have to introduce any additional theorems to describe the Booleans. Our Boolean extension still has all of the rules of lambda calculus. So these Booleans did not add any theorems, all theorems which apply to lambda calculus apply to these guys, right? For this reason, it is useful. The reason this is useful is that anything proven about lambda calculus is automatically true of all conservative extensions, right? That's the purpose of a conservative extension. It's like, if you haven't changed the theorems, then anything proven with those theorems still holds. Because we have not changed anything about lambda calculus by introducing these Boolean terms, we don't have to worry about them when we're producing proofs of things like determinacy. It's a cool result. It's a cool result because you have to do less work, not more work for once. So. So let's think about Boolean AND. This is fun because this is something that we didn't even add. Oh, I've got a question about the previous slide. Could I explain what any theorem of T2 in the language of T1? Yes. So, yes. So any of the okay. Let's imagine T2 is lambda calculus with Booleans. Let's imagine T1 is lambda calculus. We don't, strictly speaking, in pure lambda calculus, we do not have these labels, right? So we would have to relabel our true and false terms according to their definitions under pure lambda calculus. We have to do that anyways in order to compute them, but we would have to do that to express what T2 is expressing in the language of T1, right? It's possible, it's just rewriting, right? In our case, it's just rewriting. Yeah. Joe says, I think it means no meaning was changed. Something was just relabeled or written differently. Yes, that's a fair assessment. So we didn't have an AND operator in UAE. All we had was if then else. That's because we wanted to keep that language as small as possible. Using conservative extension, however, we can add basically our full complement of Boolean operators to lambda calculus without having to incur any penalty with respect to proof length or difficulty. So, let's define an AND operator. Since adding language elements is so easy, let's add a few more. So here's AND. AND shall be defined as lambda B, lambda C, BC false. So just for the sake of, like, you know, because I know it's like the next question that's coming is like, am I going to be expected to memorize all of this? You're not going to be expected to memorize all of this. I wouldn't expect myself to memorize this, so I don't expect you to. I expect you to know where to find the information should you need it. The reason we're doing these is not so that you know not so that you've memorized the formula for AND. The reason we're doing these examples is because we are now trying to move our abstract knowledge of lambda calculus into something more practical. I'm trying to show you guys that you can actually program in this stuff. And, you know, it's like practice with, like, how these things work as well. So, but yeah, this is some proper brain-melting stuff. By the time we're done this lecture, you should feel it running out your ears a little bit. So, perfectly normal. You don't need to consult your doctor, unless that's actually happening, in which case you need to consult your doctor. So, AND. Lambda B, lambda C, BC false. With input true, true. Right? So let's do this on true, true. See if it comes out with true. I mean, you can see that it does, because, you know, obviously, it's on the page there. But the more interesting thing is how it comes to true, right? We need to start thinking lambda. So, first thing we do, of course, is get rid of this first lambda, apply using this argument. So, argument gets applied, replace B for true. There we go, true. Next, do the same thing with C. Apply true to C, replace it there, we get true, true, false. Good. So far, so good. Now, we are applying true. So, before we apply these, we need to expand the definitions. So, that's lambda T, lambda F, T, true again, and then lambda T, lambda F, F. So, take the first, take the second. You should, maybe you see, at this point you should be like, oh, that's why. Yeah. So, this one takes the first. What's the first? It's true. Boom. So, you apply this guy to T, right? So, true gets substituted in here. So we end up with lambda F of lambda T, lambda F T, which is true. We apply false to that. That gets rid of this secondary lambda F, right? And we are left with simply lambda T, lambda F T, which, of course, is our definition for true. So, true and true yields true. So, let's do it again. True and false this time. So, it's the initial substitutions are the same. We end up with true, false, false. Right? So, lambda T, lambda F T, that takes the first of two arguments that are applied. The first one is this guy. The second one is this guy. This guy, this false, gets substituted in. This one makes the F disappear. We are left with lambda T, lambda F, F, which is, of course, our definition of false. So, true, false is false. There we go. Ah, we have a question. How do we know how many arguments and takes? When we apply something to lambda b, lambda c, b, c false, but what happens when we try to apply true, true, true? Is it just the number of lambdas? Yes, it's just the number of lambdas. Yup, that is it. You know that and takes 2 arguments because it has 2 lambdas. It's as simple as that. Can I explain the second to last step again? Sure. So, I'll go through all 3 of these. So, lambda t, lambda f, t, right? You take this guy, which is the argument that's being applied, because, again, we start with leftmost, outermost, right? We substitute that in for t, right? So that's the substitution. You then take this guy, apply it as an argument here. That blows out the f. There's no f here that's not, like, so this is where the binding comes in really important, right? Because you might be saying to yourself, well, I've got an f here. I'm replacing for f. There's an f here. Why am I not replacing this f with this guy? And the answer is, because it's bound to this lambda. It's not a free occurrence of f. You must only replace free occurrences of f. So this lambda f just disappears because there's no free occurrence of f here to perform a replacement with. So then you're left with just false, which is this guy. So there you go. Technically speaking, I could have, like, not expanded these guys, and it would have, like, these guys don't actually get expanded or at any points, or, like, they're not used, really, so it's not important. They could have been left as false, I suppose. Maybe in future I'd do that, but yeah. Ah, there we go. Haha. Yeah. Yeah, as Yusuf points out, I've expanded things I'm not using, which, you know, that might make it a little more confusing. I apologize. Later on, I get onto that, not expanding things I'm not using. But incidentally, this stuff is not out of the textbook. So if you're thinking that, like, I'm only showing you stuff in the textbook, it's like, no, I'm actually adding to the stuff in the textbook as well. This is, you know. Anyway, so hopefully you guys get the idea at this point. Let's just go quickly through the other 2 cases. Since it's and, we can do this really reasonably quickly. So, what about false true? What if we apply false true to and? Well, perform the initial 2 substitutions, and you get false true false. Right? So, take the second, take the first, take the second. Right? So we apply this guy to here. It gets rid of the t. We're left with lambda ff, which is, of course, the identity function, which results in just false. If you apply false to the identity function, you get false. There's some math going on in the chat. I need to see what's going on here. The third argument you listed remains outside the and function, so you would then return true, true, and then the true absorbs the other true. So you get lambda t, lambda f dot t true, which subs in, you just get true. Yep. So basically, and true, true, true yields true, true, and well, okay. Let me see here. That might not be correct. So let me just steal your lambdas here. There we go. So, if you applied... So, if you had and you applied true to it, right? And if you had one more true in there, say, right? That's what the question is in the chat. Like, what if you throw one more true in here? What you would end up with, well, you'd end up with the result. Let's see. Copy that. Oh, get out of here. Paste. True, true, true. So we perform replacement 1. Get rid of that. Copy, paste. Next, we perform replacement 2. Get rid of that. Doop-a-doop-a-doop. So we're left with true, true, false, true, which, you know, this true will absorb 2 arguments and take the first. So this gets applied. So basically, you end up with true, true after this. So what happens when you apply true to true? That's an interesting question. You get, well, let me just grab this guy right here, right? So what you end up with is this. You get lambda f, lambda t, lambda f, t. So you're getting something that's still expecting one more argument. So this is neither true nor false. This is another term. So there you go. I think it's much easier to read if you don't expand anything. Yeah, it's... If I have time to redo these slides, because, you know, I still have next week's slides to make, primarily, so... In next week's slides, I'll try to minimize the amount of redundant expansion. But yeah, so this is how it works, right? This is how all this stuff works. Both of these cases are going to end up with false because false will always select the second one. If false is the first thing being evaluated here, it's always going to select the second guy, which is always false, so false is the result. That's how AND works. So that's good. We got one more thing before we close off this section. Pears. And I'm not talking about delicious pears, the type that you buy at the grocery store. Terrible, terrible, terrible. Yeah. Yeah, good. So, using the selectivity of Church Booleans, we can easily use them to encode pairs. So, a pair is a function taking 3 arguments, b, f, and s. It's startlingly similar to the test function. Really, the only difference is the last argument in is the one that gets put in front, right? And then you also have two additional functions, first and second. All these do is apply true or false to a pair. So the idea is you apply 2 arguments to a pair to get a pair, and then the pair can be selected by using the third argument. You can select either the first or the second of them. So B is used to select between F and S. First and second merely apply true and false respectively. Since true selects the first argument, it also selects the first term in the pair. Likewise for false. Cool. So, there we go, sorry. Any questions so far? What time is it actually? 10 minutes left. Not enough time to get through this whole section, but we'll try. Well, no, we'll take it. We'll take it at a good pace, or as opposed to a fast pace. So far, so good. So, could I explain how B is used to choose between F and S? Yes, okay. So, let's do a quick example of this one then. Before we get into church numerals. So, let's grab this. Copy text. There we go. So this is our pair. This is our pair encoding. So, first, we need to set up the pair, right? So let's imagine that we have two lambda expressions. Let's call them let's call them A and B, right? So we have to apply two arguments to this to get like a properly defined pair. So that will result in the following. If you perform I'm doing two substitutions at once here. Oh, I'm already using B. Gosh darn it. X and Y then. X, Y. Right? So whatever X and Y are, they could be any arbitrary lambda expression. They've now been stored inside of a pair. That's one way of thinking about it. Even though lambda expressions don't really do storage. They're in there. So, if you apply true to that, what you end up with is you end up with true xy. True, of course, selects the first one, right? Because it's, well, it's this guy right here. Lambda t, lambda f, t. You apply that to xy. It takes the x, leaves the y. So that's why first works, right? Because what first does, FTS or FST, it takes p. It takes some argument p and applies true to it, right? So if we were to take this pair here, right, apply that to first, you end up with this guy substituted in for p, right? And then that's true applied to the pair, which, you know, again, true gets replaced for b, it selects the first, there you go. Yeah. There you go. So hopefully that suffices for an example. I realize it's not in the slides, but, you know. That makes sense. Good. The trick is encoding all of your data first and then in passing a function to it. I can imagine this working on a class like objects where you encode all the data first and then allow it to take some member function. Yeah. Yeah, you know, think functional though. Don't think imperative. Like you need to start developing the ability to think purely functionally, because that'll help you on the assignments. And if you like, it's kind of like learning a foreign language, right? It's like if I'm trying to learn, like, for example, Polish, right? There you go through a phase of having to translate every word from Polish back into English, and then understanding it in English, and then retranslating it from English back into Polish. But the better way to do it, like, once you've done that long enough, there's much less, like, mental taxation that goes on if you can think in Polish. You know, it's like you cognate using Polish phonemes, and then you can produce Polish as a result without having to run it through English first. It's like this is the same thing with functional languages. It's much better to be able to think in functional languages than to be able to have to route it through an object-oriented paradigm for you to be able to understand it. Fortunately, this is like more or less the way that math works, so it's, I think Lambda expressions are easier to learn than Polish. More vowels. Yeah, cool. So that's pairs. We didn't make it as far through this as I thought we would. But then again, I guess, like, last time we had, like, one section left over at the end of the week, so it makes sense. So, before we depart for the week then, let's talk briefly about how you would go about encoding numbers. We've done the Booleans, now let's do the numbers. We can define the natural numbers in lambda calculus in a manner still quite similar to piano arithmetic. This is how we define our church numerals. 0 is lambda s lambda z z. 1, or church numeral 1, is lambda s lambda z s z. 2 is s s z. 3 is s s s z. You may pick up the pattern. Yes. In other words, church numerals take two arguments, a successor s and a zero term z. Z is applied to s, and the result is applied to another s, and so on until we reach n applications. So that's really what it is. It's like whatever the number is you're representing, that's how many applications you have inside of these numerals. Of course, notice that we have to apply them in reverse order. Reverse associativity. Pardon me. Like, normally this is left associative, but for these guys it has to be right associative, which means that we end up doing a lot of brackets because, I can't just put at the top of the slide, by the way, on this slide, on this slide only, lambda calculus is right associative. That would just be terrible. So we end up with a lot of brackets. But, yeah. Correspondence with Booleans. So, an observant student may have noticed that C0 has the same definition as false. This is true. Remember, it's lambda s, lambda z, z, and in the case of false, it's lambda t, lambda f, f. Ta-da! This is sometimes called a pun in computer science. I just had to tell you this because, as a big fan of puns, I have to point out when we have an actual legitimate pun in our midst. So the same thing happens in a lot of lower level languages, like C, where the interpretation of a sequence of bits is context dependent. A lot of languages do these sorts of things. In C, the bit arrangement 0, all zeros, corresponds to, among other things, the zero the integer, false the Boolean, and a character array of 4 null characters. Assuming you're working with... or wait, no, it would be 8-bit. Would it be 8? It depends on the encoding. If it's UTF-16, then it's 4. But, yeah. You don't get the pun. The pun is false, i.e. 0. That's a pun. Isn't it funny? This is true. No, it's false. Yeah. Anyway, so, I think that's as far as we'll go for today, considering we're out of time. Looks like we lost some people on church Booleans. Hopefully we can keep that number above 60, keep the number of people still following above 50%. Yeah, again, I can't help you if you don't have a question. If you, like, I can't help you if you don't have a question. But, Yeah. The material is what it is, you know? Any other questions before we get out of here and have a nice weekend? Turns out puns in computer science are about as funny as puns in general. Who would have thought? Ha! You wound me, sir. You wound me. Okay. This is. Oh, I just got a real question. I was just gonna about make a like a grand philosophical claim about humor, like, but I'll answer the real question. Does this language use denotational semantics? No. This language uses operational semantics. You could definitely come up with a denotational semantics if you wanted to, but no. We're still in the realm of operational semantics. Hey, Prof. For assignment 3, is the idea of question 1 to demonstrate your evaluate rules hold for the 5 theorems, or are you only looking for you to list them? No, it's more like it was. That's like adding addition, right? Let me take a look at it for a moment. Assignments, A3, bloop. Please make the claim of humor also. Yes, I will. Oh yeah, no. My observation of puns is that puns are the working class of humor. By far the most common, underappreciated, and sniffy people think they're better than them. Ha! Take that. So, A1, question 1, adding addition. Ah, yes, so this is not so much, like, I'm not looking for you to prove anything with these. So, like, please, 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 please don't come up with new proofs for all of these. I don't want you to come up with new proofs for all of these. I'm merely giving them to you as reference because they're design constraints, right? It's like, when you design your addition operator, please make sure you don't break determinacy. Please make sure you don't change the fact that every value is a normal form. Don't make it so that you can have something with, like, don't have a normal form that includes pluses unless it's, a type error. Stuff like that. Like, design it so that it fits the language. That's what I'm trying to say. Yeah, so that's what I'm trying to say with question 1. I'm not asking you you to redo all of these proofs. I'm not asking, like, all I want is you to propose some new syntax, which should be easy, propose a few new semantics, like a few more rules of evaluation that you could add to the operational semantics. They should be in line with the existing ones, right? That's what I'm saying, basically. This component of the assignment dates from a time when it was longer, and it was a question in the textbook of, like, if I add this rule, does it change whether or not these theorems hold? But yeah, I didn't ask it because the assignment was too long. So, sorry, if you have time right now, could you give a quick overview of what exactly we are trying to do in question 2? Yeah, so question 2, if you remember the topic 3 slides, right? Or whatever, topic 3, topic 4, what topic are we on again? Topic 3. So, this guy, this big fat bastard, the determinacy of single-step evaluation. Remember how we did that proof and we went through it in a fair amount of detail, and it was an entire section in topic 3? I want you to take that proof, expand it so that it also applies when you add the rest of the evaluation rules in UAE, right? So the evaluation rules added by prove that this result still holds for UAE when we add our semantics for arithmetic expressions. So when we added arithmetic expressions, we got added like 5-ish new theorems, new evaluation rules. It's like, take the proof that I gave you, expand it so that it also takes those new rules into account, right? Prove determinacy with this expanded set of terms and rules. Noticing question 2 is asking for a proof of the value rules in the context of the determinacy. Yes. This is, you should make a proof. A proof is your deliverable. One proof. It's a beefy one, right? Because there are a lot of terms. But like most of the cases are meaningless anyway, so you can say this case is meaningless, this case is meaningless, that case is meaningless. This guy, it's like you should have an EBNF grammar, which is very small because it's only one operator, and you should have like, however many theorems it takes you to encode the semantics. Probably no more than 3, Like, look at the other operators and see how many theorems it takes to define one operator and use that to sort of inform your decisions. Does this mean that puns are going to unionize? No. Actually, like unions for actual working class type jobs are not the ones that are, not the ones that are doing well these days. It's mostly like the unions for like the teachers and people that, I wouldn't necessarily consider to be, working class people. It's not like a welders union, the union of teachers. But yeah. No, I don't think the puns are going to unionize. So, could I explain why this language uses operational semantics? You don't really understand operational semantics. Yes, I will answer that question. I have one more question about assignment 3, so I'll do that first. So just be clear, this expanded set of terms isn't from our question 1 answer. No! Oh yeah, that was a question I got on Piazza. Although this question comes after this question, I do not expect you to include your addition operator in question 2. I do not expect that. If I wanted that, I would have stated that explicitly. No, you don't have to prove determinacy over your addition as well. Just UAE as given in the slides. So, good. And question about operational semantics. So, that kind of gets into like what the definition of operational semantics even is, and I think I've got them all in one place on the project, so I'll just pull that up. Oh yeah, guys, did you see what the... Look what your professor is working on. Aren't you excited that your next project will be to implement untyped lambda calculus in Haskell in pretty much the same way that you've been doing UAE so far? Ha 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 ha. There you go. Not even Mark knew about that one. Wah. So. So there we go. So these are the operational semantics of untyped expression language, right? So with denotational semantics, what you're doing is you're trying to take the terms of the language and map them into some set, some carrier set. It doesn't really matter what that set is, but that's, we're trying to find what are called semantic domains. It's a completely different style of doing semantics than this is, right? With denotational semantics, you're not necessarily, you're not trying to define, evaluation rules. You're trying to find, some mathematical entity that you can draw correspondence to that already has the rules in it, right? If you apply, if you can find a correspondence between the terms of your language and the natural numbers, then you get all of the theorems about the natural numbers they apply to your language, so long as your correspondence is correct, right? It's a way of avoiding having to state all of it explicitly. The difference with us, what we're doing with operational semantics, we are coming up with the specific set of evaluation rules itself without having to make reference to anything else. If you take as, if you take this as the basis for the mathematics, right, you can build up all of the operational semantics without the need to refer to any larger sets of theories, right? You don't need, we don't even need propositional logic in this, You may have noticed that, when we do proofs with this kind of stuff, we make occasional reference to propositional logic, but only insofar as that's the meta language of sets, right? It's these guys themselves, it's we have defined things in a very, very minimal fashion, and it's self-contained, right? So the reason it's called operational semantics is because what we are doing is we are defining theorems which tell us what the operations are. We've designed the semantics in terms of operations. Now, whether that's a single-step operation or a multi-step operation or a big-step operation, that's sort of, we're going to talk about single-step most of the time because it's the easiest to use and understand. But, with the Booleans, if you have a set that contains these terms and you have these rules, that's all you need, right? You don't need to make reference to the Booleans as they exist. You don't need to make the Booleans that exist in, first-order logic, your carrier set for this. It's self-contained, right? And because it's self-contained, the proofs are shorter and easier. But yeah, so hopefully that's kind of an explanation. We're not using denotational semantics largely in this class at all. All of this business that we've been talking about, what is an evaluation rule? What is a multi-step evaluation rule? What happens, does the evaluation rule have this property? Does the evaluation rule have that property? The conception of an evaluation rule as a relation on sets is operational semantics. That is operational semantics. In operation, so to speak. If you were doing denotational semantics, you would be coming up with a mapping between your terms and some carrier set, some semantic domain. So, hopefully that's an explanation. Is that a good explanation? It was a... Oh my, I'm going over my time, but... Is that good? Sehr gut. Jawohl. Okay, well, I think that'll do for me today. Take her easy, folks. Have a nice weekend. Oh, there are my chat. Okay. So denotational semantics just refers to some other operational semantics. No, they're different categories. They're different, like... Saying denotational semantics is just some other type of operational semantics is like saying, it's like saying that, like, biology is just another form of chemistry, you know? And, like, there is a little, like, there might be a grain of truth in that, but, like, you're definitely stretching definitions. No, you should think denotational semantics are a completely different thing from operational semantics. They're both expressed in the language of formal mathematical logic, but they're definitely different approaches. Like, they're different methodologies. Are the new evaluation rules what we are trying to prove determinacy for in A3? These guys. This guy. See, it's B, N untyped. This second one extends B. This is it. These 1, 2, 3, 4, 5, 6, 7 new rules. That's what you're trying to expand it to include. Alright, I'm going to log off here. Take her easy, folks. Have a nice one.